video, we're going to talk about sun cycles and Earth orbit. So we're in solar cycle 25, and the minimum occurred in December of 2019. It had a fairly slow start, but the maximum is expected to peak somewhere between 2023 and 2026. The projections for that maximum vary drastically between agencies, but there is a risk that it could become an extremely powerful geomagnetic storm. A good example of a magnetic storm of this capacity could be referred to as the Carrington event, which is a powerful geomagnetic storm that happened in September of 1859. It occurred during solar cycle 10. It had a solar coronal mass ejection that hit the Earth's magnetosphere and induced the largest geomagnetic storm on record. It created auroras that were seen in Australia, the Rocky Mountains, and the Caribbean. The energy was so powerful that it knocked out several telegraph services and even gave operators an electrical shock. It also took out several electrical pylons, which threw sparks. Naturally, we have massively progressed in our reliance on electronics since that time. Unfortunately, due to that reliance, these electronics and power solutions are likely going to be compromised during the next solar cycle if it reaches a maximum that is projected at the extreme ends. We're going to talk about Earth orbits, and I thought about putting together a video, but then I stumbled across this one from Scott Manley, and it's lengthy, but it's all pure gold, so highly recommend it.
This is the Earth, obviously, and I put a satellite into it. I have actually adjusted the Earth so the rotation is around the North Pole exactly. Obviously, the Earth has an inclined orbit, but the game engine, likes to use the universal grid as its reference system for inclination. So anyway, yeah, there's basically no satellites that go on this orbit, and the reason is that to get a satellite into orbit, you have to go from a launch site, and the minimum inclination that you can access is that of the launch site. So the Kennedy Space Center is right up here. That's about 30 degrees, so I have to, minimum 30 degrees to be able to launch the minimum 30 degree orbit from this. And yeah, there that goes. So if you went for the most efficient orbit using the least amount of rocket fuel, that would be roughly the kind of orbit you would end up in. Now, there are many satellites that might do that just because they want to be in space and they want to get as much mass into space as possible. But many Earth observing satellites, they want to cover more of the Earth, and if you look at it, of course, this is only going plus or minus 30 degrees. Anything north of this, the satellite is not going to pass over, so they might go to higher inclinations, therefore, so that they can cover a lot more of the Earth with the things that they are sensing. You see, this satellite orbit is more or less fixed in space, and the Earth rotates underneath it. The ground track is what many Earth observing satellites are interested in, and so they will pick something appropriate. Now, the inclination of the space station is actually about this far north. It's about 52 degrees, I think, off the top of my head. The reason it's so far north is because it has to be able to launch hardware out of Baikonur. Baikonur is somewhere around here. Roughly like that. And to actually launch, they have to be careful they don't just launch eastwards, because then they would drop rocket stages on China. So they actually launch to the northwest, and that is why the space station is at such high latitudes. It's not efficient for the US to launch stuff to the space station out of Florida from this latitude, but they do it because it's an international effort and they want all the partners to be able to reach the space station. But of course, if we're interested at looking at the surface of the Earth, then we won't get anything above 52 degrees. So if you want to see all of the Earth, you have to go all the way up to about 90 degrees. I've got 90.3 but that is pretty much an accurate polar orbit. Now, this particular one is lined up with the day-night of the Earth. And the thing is, the Earth is actually also moving around the Sun, so you have to imagine the angle of illumination is actually changing over time. So if you imagine, what's going to happen is over time, the day-night is going to shift. And this may be fine, but it may not be, because your spacecraft is going to have to deal with different illuminations, different solar panel illuminations. What it's looking at on the ground, maybe you might be looking at it at different times of day. So there's a special type of orbit called a sun-synchronous orbit, where this actually freezes, this actually tracks the sun. And that is at an inclination of about 98 degrees. Now, 98 degrees is more than 90, as you've noticed, and that means it's actually slightly retrograde. So the way the sun-synchronous orbit works is that the Earth around the equator is slightly oblate, it is fat, and that extra girth down here wants to pull the satellite orbit down towards the equator, so it would actually want to pull it down like that, but, the satellite in its orbit actually has angular momentum. So instead of getting pulled flat, it starts to rotate around the longitude of the ascending node, starts to rotate like this. And if it just happens to match the rotation of the Earth, or the orbit of the Earth around the Sun, then the solar illumination will remain the same. If you want to see the complete details on it, I did a video called The Fat Earth Theory, where we explain this in more detail. Suffice to say, about 98 degrees is going to get you on a sun-synchronous orbit, and that is highly desirable. Now, you can actually go to even higher inclinations, but the problem with higher and higher inclinations is that you'll notice as this thing flies across, it's actually going backwards relative to the Earth. This is a problem because it means that you're actually having to put in more velocity at launch. So there's very few satellites that go in such highly retrograde orbits, but there is at least one nation I can think of that launches satellites onto retrograde orbits, and that is Israel, because they are at the east end of the Mediterranean, and all their people to the east of them are people they don't want to annoy, so they don't want to drop satellite stages on them. So instead, they actually launch spacecrafts, out to the west across the Mediterranean. So that's one strange example of how satellites might end up on highly retrograde orbits. One of the most desirable classes of orbit is the geostationary orbit. And the great thing about the geostationary orbit is its period exactly matches the rotational period of the Earth. That is 1436 minutes, or roughly 23 minutes 56 seconds, because of course I'm talking about sidereal days, that is the rotation with respect to the stars. You have to account for that 4 minutes every day is due to the Earth moving slightly around the Sun. So yeah, as you go further out, the orbital period gets longer and longer because the distance you're traveling gets longer, but also the force of the Earth's gravity gets weaker and weaker, so the spacecraft can move slower and slower. And at about 35,750 kilometers above the surface, at that point the period of rotation, the period of the orbit, matches the period of rotation of the Earth. So you can sit here, and from the Earth's point of view, it looks like this spacecraft is more or less sitting above, some part of Central America. Just continuously just hanging there in space in exactly the same way that bricks don't. But actually this is, a brick sitting here would in fact do that, because any object placed into a geostationary orbit will stay there. So these are highly desirable. They only work if your inclination is 0, because then otherwise you're going to move up and down, and your spacecraft are going to, or your satellite dishes on the Earth are going to have to track it. But the nice thing is, you can have a dumb fixed satellite dish that points exactly at the same place in the sky continuously, and it will track this. So geostationary orbit gets allocated based on countries' claims, and it's not uncommon for countries that have access to essentially lease out their slot in the geostationary ring. There's a number of satellites up there that are doing communications. There's a couple of weather satellites. There's quite a few. There's Himawari, there's GOES 16 and 17. So, it's quite a busy place. Now, the problem with geostationary orbit is you cannot really cover higher latitudes. If you get down close to the Earth, you see that there's a part of the Earth where, if you're imagining me sitting on the surface, the satellite's going to be very, very low on the horizon. And in fact, there's a point above, 81 degrees north where you cannot actually access geostationary satellites. So people working at polar stations cannot see geostationary satellites. And if you imagine, well, why don't we just make them go north and south? Well, that would be an inclination, say, of, 80 degrees. Let's do that. Well, what's happening is it goes up above and it goes down below, and it doesn't stay still anymore. So it is geosynchronous, but is not geostationary. To get those high latitude communications, you need a different kind of orbit. So this glorious ballet of satellites is what we would call a Molniya cluster. It is a solution to provide telecommunications for high latitudes. So if we say look at up in the tundra in the north of or north of Canada and all that, they can communicate with Molniya 1 right now, but it is about to start falling back down. But the good news is that Molniya 2 is currently rising, and it is now providing the telecommunications. So the great thing about this design is that as these things are on highly eccentric orbits, they come out, and when they're out at apogee, they are moving very slowly, so satellite dishes can track them without moving too quickly. And they, of course, provide continuous communication at these high latitudes. Of course, the big downside compared to geostationary orbit is the satellites are not stationary, so the satellite dishes on the ground have to be smart enough to track. Also, they have to be able to switch across satellites, because one satellite is about to start dropping down, but the good news is another is rising to take its place. So the satellite equipment on the ground will switch over, and continuous communications at high latitudes is possible with this kind of cluster. So the important numbers here are the period is 718 minutes, that is half a sidereal day. The inclination is 63.4, and there's a very special reason for that exact number. The eccentricity is 0.74, so that gives them a fairly large range. At the high end, it's going all the way out to geostationary orbit, more or less. And also, the argument of perigee is about 270. That means that they are as far north as possible when they reach their most distant point, when they reach apogee. If it was the opposite of that, if it was 90, they would be reaching apogee in the southern hemisphere. So the reason for the 63.4 is to do with the oblateness of the Earth. Now, we've already seen that the orbits of a sun-synchronous satellite will be twisted around, right? That's what's the changing there is the longitude of the ascending node, but it will also affect other parameters on an eccentric orbit. In particular, it will affect the argument of perigee. And if that is the wrong value, what will happen is this thing will get twisted around over time. But the scientists that figured this out, they accounted for this, and it just happens that if you use 63.4 with these orbital parameters, then that particular effect gets completely cancelled out. So that's why you have to use 63.4 degrees with the 12-hour period and the eccentricity of 0.74, and then you get continuous communication. These class of orbits were first used by the Soviets in the 1960s to provide communications using their Molniya satellites. That became the name of the satellites, and it also became the name of the launch vehicle, which was a variant of the R-7 that we now know today as the Soyuz. The Molniya rocket actually continued launching right up until 2010. The US military also uses Molniya orbits. In particular, there's the Quasar system, also known as the Satellite Data System, which uses these for high-latitude communications. And I also understand that there are some signal intelligence satellites which use these as well. I mean, after all, if you're going to track communication satellites, you're going to be forced onto the same orbits as them if you want to get close to them. An alternative to the Molniya orbits is the Tundra orbits. Now, Tundra orbits are pretty much the same 63.4 degree inclination with the high eccentricity, but the period is 24 hours rather than 12 hours. So these, I know, they move a little more slowly across the sky, and they have been used. The most notable use I can think of is the RadioSat 1, 2, and 3, which were used by Sirius XM Radio for a while. I think they have switched back to purely geostationary satellite service. But yeah, for a while they were certainly using satellites in this kind of orbit. So same values as before, but the period is now 24 hours. So, you get these close passes as they hand off from one satellite to the other. Okay, so the final set of orbits I want to talk about are the intermediate orbits. They're between low Earth orbit and geostationary orbit. Now, I've actually used Universe Sandbox to create a ring here for the geostationary orbit. And this ring here, this is actually supposed to be roughly the range of the Van Allen belt. So these satellites out here, this is supposed to represent the GPS cluster. The GPS cluster has 6 different orbital planes, and there's like 4 satellites in each, plus a number of spare satellites that are available. They're inclined at 55 degrees. Obviously they rotate 60 degrees around for each different plane. But the idea is that you should be able to see 4 GPS satellites all the time, no matter where you are. These are up in these orbits because they want to be high enough that they're easy to see from the Earth, but I guess not so high that they're dealing with geostationary or stuff or whatever. It just seems that, I guess that was a good altitude for it, because GLONASS and Galileo and Beidou and all that, they're all using the same, roughly the same intermediate orbit altitudes. So yeah, Universe Sandbox. There's many other things you can do with it, and I should probably use it a lot more, but I thought it was useful to illustrate these different orbits so you can actually get an idea. I'm Scott Manley. Fly safe.